Swayam Prabha. Digital India. Educated India.
Now that we have understood the non-uniform axial loading, we will go ahead and solve a particular problem. So the problem that you have over here is that you have a bar which is hanging from the top. It is clamped at the top over here and it is being pulled by a force P. But unlike the problems which we looked at, this bar now has some amount of self-weight, right? So previously we looked at in all the examples that had no particular self-weight, and as you can tell that if this bar also has no self-weight, then the deflection at the very end over here is simply going to PL divided by AE, right? Very, very flat example. But now you have that if you look at the question that you have to find the end deflection, that is the delta that you are trying to find. So this maybe I'll mark it as that is the delta that you have to find. If the bar is hanging under its own weight, so it has a self weight of its own, and this gamma is given, which is the unit weight of material, and in addition to that it is also supporting this particular load P that is there, so which is the end load over here, right? Okay, so now how do we do this? So now we have this load which is sort of percolating from the top all the way to the bottom, right? So suppose if at a distance x we take a a section over here or an infinitesimally small element dx. Now if I have to maybe write the equilibrium equation for maybe just this particular part that is there, just to calculate the internal forces. So remember, you have to calculate the internal forces at every step now. Because it's not just the end load P, you have this self weight of the material which is also there. So if I take this particular section and maybe if I draw just the free body diagram of that particular part, what I essentially get is that suppose this is my the bottom part where I have this load P which is acting over here, and I have this internal weight that is the small self weight which is acting. So this self weight is nothing but your gamma, right? It is gamma times the area of cross section A and this particular length. So the total length of the bar is L and we have this X over here. So this particular length that you have is L minus X, right? So it is gamma A times L minus X, right? So to balancing all of this, you have this internal force, right? N over here. So N at X I'm calculating. So N of X is nothing but equals to gamma times A L minus X plus the load P, right? So these are all acting vertically down, so N of X is vertically up over here. Now another way to get N of X, since you guys love doing integrations, another way to get this quantity is how do we get it? The other way to get it is you take this infinitesimally small length dx over here and you essentially integrate from x to L. So another way to get your N of X, if I have to write in that way, will be integral from x to L, right? We have gamma A dx plus P, right? So if you do that, you will get gamma A times L minus X plus P, which is essentially equivalent to what you got over here, right? Same thing. Yeah. So now that we have the N of X, what we are trying to find is the end deflection delta, right? So let's write the formula of that one. So we have delta or the d delta for this small element dx. We calculate the d delta, then we integrate from the top to the bottom. So we have of our d of delta is simply going to be N of X dx divided by A times the area of cross section is the same. It is this formula is equivalent to PL divided by AE. I'm saying this formula over and over so it gets ingrained in your memory. It's PL divided by AE. So we have this d delta over here. So from this one, if we have to sort of calculate the delta, what you get is integral. Now we have to integrate from the top to the bottom, that is 0 to L n of x dx divided by a of e, right, where n of x is simply this guy over here. So if I have to write it further, so it is going to be your delta will be equal to, I can pull out the ae outside the integral because it's a constant. So I have 1 by ae integral of 0 to L gamma a times L minus x plus p, and this entire thing with dx over here. Right, so let me scroll a little down. So if I do the integration, what I will get is 1 by ae, the one which was outside the integral sign. If I do the integral, what I will get is your gamma a L square minus gamma a L square over 2 plus p times L, right? So if I simplify this and pull this out of the out of the parenthesis, what I will have is that for the first term, for this one, your a and a will cancel over here. So what we will get is gamma L square by 2e, right, plus PL divided by AE, right? So this is my eventual delta that I get. So this is my final answer that I have. But while I am marking this, I want you to introspect a bit. I want you to introspect and think that does it logically make sense? For instance, everything is a positive quantity. So yes, in addition to just having this load P over here, because you have a cell weight, you will have some additional deflection, right? But suppose the bar was weightless. If the bar was weightless, so essentially, gamma is 0, you don't have a unit weight. This formula reduces to PL divided by AE, which is exactly what we had learned. If you have a weightless bar with a force P, the delta is PL divided by A. So that chalks out. That makes sense over here. So if gamma was 0, so it was delta is PL divided by AE. And now since you have a bar which has some amount of self weight, you're getting this additional deflection that is over there. Another important tip which I want to give you is that once you have the final answer, always check the units that you have. If you check the units of this one, it will be in the units of length, that is, mm or inch or so on. And if you put this gamma and L square and things which cancel out, and if you put this E over here, you must ensure that, or you can check that the unit of this quantity must also be mm or inch. So you have oranges compared to oranges, and not oranges and apples, that you have two dissimilar units which are sort of coming together and giving your final data. So these are the some of the other finer checks that you can do, right? So I hope this problem example was clear. So we had a bar which was hanging of its self weight and this load P, and we sort of took a small section, we found out what is the internal force that is there, and from that we calculated the overall deformation delta that was there. The next, what we're going to look at are actually loaded structures, but which are also statically indeterminate and also thermal stress problems. So what we have essentially, if you recall until now, that we had looked at structures which are statically determinate. For example, from the equations of equilibrium, you can figure out what are the reactions and what are the forces which are acting in the system. We're going to move on to structures which are statically indeterminate. Now, before we do that, and let's go back to understanding how statically determinate structures behave, what we have looked at until now. So what you have over here is that both in this particular structure as well as this one over here, you can easily calculate these reactions which you see over here. For example, here R is going to be simply P1 plus P2. Here your reaction at this point B is simply going to be equals to this load P over here. Now, while we are at this slide, can you maybe guess that what is going to be the deformation of this AC? It is essentially not going to have any deformation at all, because all the internal stresses in this member are going to be in this member CP over here. Sorry for the short digression, but these are some of the interesting tidbits which you might notice while you look at these problems over here, right? Now next, compared to these statically determinate structures where the equilibrium equations are sufficient enough to solve that particular problem, if we go ahead and look at statically indeterminate structures, for example, the one that you see over here, as well as this figure over here. So if you see this figure, it is clamped at the base and it is clamped at the top. So it's a fixed condition, right? And you're applying this particular load P, intermediate, where this cross section changes, right? Now, as you can tell, that since it is fixed at the top and fixed at the bottom B over here, you're not going to have any deformation in the structure. But the question is that, what are these internal loads which we are going to have, and also more importantly, what are these reactions what we are going to get, right? And also, is this point at where the cross section changes, is it going to move up and down, right? Although the overall deformation is maybe 0, do the sections intermediate, they change, whether it moves up or it moves down. Similarly here, you have, in contrast to this one, you have a bar which is of uniform cross-sectional area A from the top to the bottom over here. Now again, we do not know what are the reactions RA and RB. Now while we are at this slide, can you maybe guess intuitively what is going to be this reaction RA and RB over here before we even solve the problem? Now maybe you have guessed it right. So this reaction RA is simply going to be P times B divided by L, and RB will be P times A divided by L. So this is just from simple intuition and guess, but let's see mathematically if we are able to derive these or not, right? So again, so how are we going to solve this problem? This is a simple example. You can have more complicated loadings, you can have different kinds of support conditions. For example, you can have a support condition where here, instead of being completely fixed, you have a spring with a certain amount of stiffness, right? So you won't get a free deformation, you won't get no deformation at all, but something intermediate. So how do we go ahead and solve these particular problems that we have over here? So essentially what we are going to make use of are these equations of compatibility. So this is important, right? The equations of compatibility, and these are displacement compatibility which we are looking at, which essentially means that your final shape or the final deformation has to comply or has to be compatible with the end conditions that you have, or any intermediate conditions if you want to have. For example, in this problem, both in this problem and in this problem over here, you see that your final deformation, that is your delta AB that you have over here, must be equals to 0. Your deformation in this part, so if I mark say this particular part 1 and this particular part 2, they may have some internal shiftings, rearrangement, but if you look at the whole structure again from A to B, that overall deformation needs to be 0, right? So again, in other words, what it means is that the change in length of the bar of these individual members, for example here for this part AC, if I do 1 and if I do 2 over here, right, the deformations of this part 1 and part 2, they may have some internal shiftings, but this overall deformation A to B, that is this delta AB, this component over here, must be equals to 0. So again, so how do we come back and solve this one, right? So here what you see, if you look at this particular problem, so again, remember that the deformation is always that PL divided by AE. We have studied that, where we substituted the internal forces and we calculate remember the case for the non-uniform loading. This is also a case of the non-uniform loading. We calculate the individual deformations, then we sum up to get the total deformation. The only difference is that here in this particular problem, the total deformation is 0, right? So here again, if I have to take maybe a section in this in this first part over here, in this part 1, right? So if I again mark this as my part 1 over here, and this is part 2, right? And here if I say draw a random cross section over here, right? So in this cross section, if I have to draw the free body diagram of this particular part, what do I get? If I have to draw the free body diagram, I have this load, this reaction, which is RA over here. To balance this one, I must have a equal and opposite reaction of RA over here as well, right? Same and same throughout. If I take the cross section anywhere just before this point, see, just to the top of C, I am going to have this internal force RA over here. So for this member delta AC, right, if I have to write the deformation of this member delta AC, where the delta AC is always having this tensile force of RA, how am I going to write that equation? So that is going to be my delta of AC, right? It is going to be the reaction, remember PL divided by AE. So here I have my force RA, right, times the length of the member AC. The length of the member AC is this A over here, A divided by A times E. The area of cross section is same throughout, so I'm going to A times E, assuming that the material is the same throughout as well, right? Now similarly, in a similar fashion, if I have to consider this particular part over here, this BC part, and here again if I take maybe a random cross section like this, and maybe if I consider this bottom part over here, you can do the top part as well. Eventually you will see it works out to the exact same thing. If I draw the free body diagram of this bottom part, so what I eventually get is that for this particular section, I have this bottom reaction which is acting, RB, right? Now, as long as I am just below this point C over here, I am to balance this RB, I am going to have this another force RB which is acting over here, equal and opposite, right? So, if I am looking at this member CB, all along just to the bottom point of C up to this particular point B, I am going to have a compressive force of RB which is acting, right? So if I have to write delta of your BC over here, that must be equal to, since I have marked this one as positive as a tensile, this delta BC must be negative that you have, right? Because it's in compression. It is going to be minus of RB times the length B divided by A times E, right? Okay. So now, what in addition to this, see, remember my end goal is to find the reactions RA and RB, right? What is the additional information that I have over here? Yes, you're right, the equations of equilibrium. What I have in these equations of equilibrium is this RA and RB pointing vertically up and this point P pointing vertically down. I know that my RA plus RB must be equals to P over here, right? So these are the three things that we have. Now, the fourth piece of the puzzle is my equation of compatibility, simple, which is that we know that my total delta AB, that is the total deformation. Remember previously what we did was that the delta was the sum of the individual deltas. Exactly the same thing here. Delta AB is nothing but delta AC plus delta BC over here. So let me just write that, delta AC plus delta BC, right, which is nothing but equal to RA times A divided by AE, right, plus minus of RB times B divided by AE again, right? But remember, my equation of compatibility in this one is what? The equation of compatibility is the top A and the bottom B are exactly at the same place, right? So this delta AB is essentially equals to 0 over here, right? So again, if I have to sort of expand this again, so what I have from this one is RA times A divided by AE, right, plus RB, sorry, I have to put a negative sign over here, times B divided by AE, right, must be equals to 0, right? Or if I have to simplify this even further, we have RA times A by AE minus of RB times B divided by AE, right, equals to 0, right? So we have two equations, two unknowns. What is the first equation? The first equation is this one over here, right? So this I am going to mark as equation number 1, right? And my second equation is what I just wrote over here. Oops, sorry. Right? Second equation is the one which I just wrote over here. This is my equation number 2, right? Two equations, two unknowns. So if you solve 1 and 2, what you will see that eventually what you will get, and you guys might want to try this on your own, you will get your reaction RA as equals to
P times B divided by L, and similarly you will get your RB as P times A divided by L, right? So this is how we solve this statically indeterminate structure under axial loading, right? So now that we have solved these indeterminate structures, another indeterminate structure which I am going to present to you are coming from the thermal stresses. So let's take a look at that and try to imagine that how it acts, right? So here you have a case of a thermal stress where you have a bar. It's a very interesting problem. You have a bar over here, right, which is clamped at the point A, clamped at the point B, and maybe you have lit a matchstick over there, you know, or some kind of a candle, and because of that you're having an increase in temperature, which is this guy delta T over here, right? Now this is a classic example where in a structure you don't have any strain but you have stresses, right? Since A and B are clamped, this bar cannot, you know, expand, right? Because you're applying a temperature, so you logically would expect it to expand, but it cannot expand, and you cannot contract if you're cooling it down. But because that it is not able to expand or contract, it is going to have these internal stresses. So our job is to find that what is this internal stresses or internal forces which are acting on this kind of structure over here. Now, how do we tackle this problem? The easiest way to tackle this problem is first to let the bar expand due to the temperature, right? And then simply push it back to what its original configuration was, right? So just to explain this in terms of figures, what we have, you see over here, right? So what we have is that this point B, which was there, right? I release this point B, and I let this point B, so I make this point B free from restraint, and I let this point B expand, right? Due to this temperature, again, I'm applying this temperature, so I'm going to let it expand to this deformation, which is delta T. Now, can you guess? You have studied in your heat transfer or your thermodynamics in your +2 that what is going to be the value of this delta T over here. So this delta T is simply going to be delta T is L times delta T times alpha, right? Or L alpha delta T, right? So this alpha, remember, it is, if you remember from back in the day, this is my coefficient of thermal expansion, right? You guys know this. So I have let the bar expand with L alpha delta T that I have over there. L is that original length, right? Now my job is, if you take a look at the original structure, this B is not moving anywhere. So essentially, by putting this support B, what I am doing is that I am restricting this movement, right? So this reaction force which must develop at this particular support, this P which is developing over here, must be resisting this movement delta T over here, right? So now if I have to take this structure and sort of push it back, if I have to apply a load P over here and push it back to where B originally was, right? So maybe just for clarity, I mark this point as B prime over here, right? Now I'm moving B prime back to B with this deformation delta P over here, which is nothing other than this delta T, because you're pushing it back by the same amount, right? So I have my delta P must be equals to this delta T that I have over here, right? Now what is delta P? Now imagine that this P that I'm applying to delta P is in a structure which has no stress, because I have allowed it to freely expand up to this point B prime. Now I'm pushing it back from B prime back to B over here. So what is this delta P going to be? Exactly right. Delta P is going to be PL divided by AE. Simple. Again, a bar, weightless bar, a bar with just applying a bar which has no stress, nothing. It is just a bar. I'm applying a force P over here, right? And the deflection is going to be PL divided by AE, right? So here, if I have to write this again, my delta P is nothing but PL divided by AE. Over here, it's a compressive force, but since I've taken care of the direction where through my pointing that P acts, points, towards the left over here, PL divided by AE must be equals to this delta T, which I've already written above. It is going to be L alpha delta T, right? So how do I find this force P? Simple. So if you take a look at this equation, this L and this L cancels out over here. So what I eventually get is this my force P over here is going to be equals to A E alpha delta T, right? Simple. So this is my eventual force that I will get. I messed up that rectangle. Let me do that again. Right. So this is AE alpha delta T that I get over here. Now remember, this reaction force, this P that you are getting over here, right, in the final structure. So this is the P. So you can imagine that along this particular side, you are going to have an equal and opposite reaction P over here. Right. So coming back to my original structure over here, if I'm increasing the temperature by delta T, I am going to have two reaction forces. Both the reaction forces will have the magnitude that I just calculated, that is A E alpha delta T. Right. So I hope that with this particular subtopic which we just covered, you are now clear with the concepts of how to solve statically indeterminate structures as well as problems with thermal stresses.